Okay, so let's get started again. Okay, so we finished up yesterday and we had gone to alkyl radical beta scission, looked at alkyl radical beta scission and alkyl radical isomerization. Okay, so from that we form these, from these alkyl radicals we can form olefinic species. So what happens olefinic species? Okay, so the addition of a double bond in an alkene molecule presents additional complexity in describing and modeling the combustion chemistry. Okay, H-atom abstraction from the beta position to the double bond results in electron delocalization in the emerging alkenyl radical. Okay, and typically the enthalpy of reaction of the initiations with oxygen molecule leading to allylic radicals is about 15 kilocalories per mole lower than those leading to alkyl radicals. Okay, so A factors are lower by about a factor of 10 due to the reduction in the entropy of activation caused by the loss of one rotation in the delocalized radical. Okay, and I'll be talking about that a little bit later. But when you abstract, so if you compare abstraction of a primary hydrogen atom in propane and a primary hydrogen atom in propene, the frequency factor for abstraction is about an order of magnitude lower in propene relative to propane because you have one less rotor in the product. Okay, so it's similar to this transition state 5, 6, 7, 8 membered ring that I was talking about yesterday. All right, so here we have a double bond in the center of the molecule someplace. So here's, I don't know, what is it? It's 3 heptene, I think. Okay, and so you have these vinylic. So these are secondary vinylic hydrogen atoms attached to the carbons here. But here you have secondary allylic radicals. And these radicals are more easily abstracted than ordinary secondary hydrogen atoms due to the delocalization. Okay? And you end up with a resonantly stabilized structure. So this species is depicted like this, but actually probably a more accurate description, if you remember your organic chemistry, okay, you've got, okay, it should be depicted like that, okay, ultimately, okay? Because it doesn't, the molecule doesn't exist as either this or this, but the electron density is delocalized across the whole molecule, okay? And you've got that delocalization, which leads to added stability of the radical compared to a regular radical, okay? So what happens these radicals, okay? It's easier to depict the radical like this if we want to consider how it will react with another molecule, okay? And typically, allyl radicals can react with HO2 or possibly CH3O2, okay? But mostly HO2 because it's in much higher concentration to give allyl oxy radicals. And those allyl oxy radicals then can decompose to give formaldehyde and something else, okay? In the case of allyl radical, you get vinyl radical plus formaldehyde, okay? And that's how we oxidize allylic radicals, okay? Typically by reaction with HO2. Okay? So again, it just shows the importance of HO2 radical. And this is just showing you it's converting HO2 into this allyloxy plus OH. Okay, a conversion of HO2 into OH radicals. Okay, so here we have the secondary guy again. We get this radical species and we get vinyl plus acetaldehyde instead of formaldehyde. But it's the same process. Okay, so we look at these, you know. Now, at very high pressures, actually, the reaction can lead to stabilization. So you get allyl hydroperoxide. Okay, you get the stable molecule formed. Okay, and then that allyl hydroperoxide stabilizes, and then with a 43 kilocalorie per mole activation energy barrier, the OO bond breaks, and then you get allyloxy plus OH. Okay, so we published a propene mechanism a number of years ago, and I forget now who did the calculations. Maybe it was Franklin Goldsmith or Judith Zador, I can't remember which, but we included the pressure dependence of that system. Okay, so you have allyl plus HO2. At high pressures, it stabilizes to give allyl hydroperoxide, which then decomposes to give allyl oxy plus OH anyway. Okay? But it stabilizes first, leads to a lower reactivity for a while, and then an increase in reactivity when the O bond can be overcome, depending on what temperature you're at. Right? So here it's just showing you in general then, the slide. If we have the double bond, we've got vinylic hydrogen atoms directly attached to the carbon atoms at the bond, and you've got allylic radicals beta to that bond. Okay? Okay, and allylic CH bonds, I keep saying it, are weaker than most others, and therefore they're preferentially abstracted and then by radicals, so they'll be the preferred radicals that are generated in olefins. Okay? However, then, its addition to molecular oxygen the bond is very weak because the energy gap between the R plus O2 and RO2 is much lower than it is, the well depth is much lower for allyl peroxy, I should say, relative to an alkyl peroxy radical. Okay? So I think I have it depicted here. So here we have R plus O2 can stabilize to RO2. I said that the well depth, it depends on whether the radical that we're talking about is primary, secondary, or tertiary allylic. But you're talking about, on average, about 36 kilocalories per mole for the well depth. Okay? Whereas if you've got an allyl radical, the well depth here is only 20 kilocalories per mole. Well, we saw it yesterday, about 19 or 1920. Okay? We won't argue over a kilocalorie per mole. Okay? Which is 16 kilocalories per mole less deep. Okay? That means that your RO2 is 16 kilocalories per mole less stable. And the system is going to be much more inclined to go back to R plus O2. Okay? It's just simple. Okay. Okay, and I had this slide yesterday. It's just showing you again here for this secondary, the well depth is 36 kilocalories per mole. Here it's 19.7. Okay, which is what I said. Okay, so that's showing the difference. And actually then you see this difference, and this is a pretty nice illustration of this point. Looking at the ignition, here we have plotted ignition delay time versus temperature for 3 hexene isomers. So we have 1, 2, 3 hexene. And you can see that the position of the double bond in the molecule makes a difference, big difference to reactivity. If we look at 1 hexene, we just take this part out. So the most easily abstractable hydrogen atom is here. We get the allylic radical, but we can also abstract other normal alkane-like hydrogen atoms in the molecule. Okay? And they will happen also. And even though this will be the dominant process, small concentrations of abstractions from these molecules will occur. That will allow addition to molecular oxygen with normal well depths, and then isomerization, formation of hydroperoxy alkyl radicals, addition to molecular oxygen, and the low temperature branching pathways. Okay? So 1 hexene, you can see, you get quite a bit of reactivity. So the reactivity increases with temperature up to about 725 Kelvin. Then you get a reduction in temperature and then an increase again, just like you would for an alkane. Okay? But 2 hexene is less reactive, and 3 hexene is very unreactive. Why? Because now, if we look at 3 hexene, we locate the double bond in the center of the molecule. The hydrogen atoms here and here are all allylic. If we produce, so we've got 2 options. Okay? They're also secondary allylic. Now, so that makes it even weaker again relative to a primary allylic. Okay? And so we form these alkyl radicals. They add to molecular oxygen, but only with a well depth of about 20 kilocalories per mole. And so we're going to get much less RO2, QOH, and low temperature branching for 3 hexene. Okay, and that's what we see. Exactly that. Okay, and then 2-hexene is someplace in between the two. Okay, so you don't, at least you have some chance here of getting some internal isomerizations in 2-hexene, much better chance with 1-hexene, but very little chance with 3-hexene. Okay, and this is a paper that was published in 2005 in the Proceedings of the Combustion Institute, and then these simulations were performed by Marco Mel. He was based at the time, I think, in Milan, but then he moved to Livermore. It was published in 2008. So you can look at those papers. Okay, this is just a slide that I asked one of my students to prepare, just to compare the reactivity. So here we have M-butane reaction. Unfortunately now it's sort of the inverse of what I just showed you. Okay, so we're plotting inverse temperature on the x-axis versus ignition delay time on the y-axis. So temperature's increasing from right to left. Okay, so here we have low temperature, high temperature. So reactivity increases here again to about 750. From 750 to 850, 900 Kelvin, the reactivity decreases, and reactivity increases again. Okay, so these are experimental data for N-butane. Here's just model predicted at different points, ignition delay times for N-pentane. Okay, and here is the reactivity predicted for 1-hexene. Okay, so why did I choose that, 1-hexene? Okay, because here we have 1, 2, 3, 4 carbon atoms here. But actually, if you just consider this part as being the allylic part, you just have like an N-propyl part, actually. Okay, so it is even faster than N-butane, even with the allylic part, but it's slower than N-pentane. Okay, so what was the point of that? The point of this is, and I'll be talking a little bit later with oxygenated species. So what does a functional group or a different group in a molecule relative to an alkane, what does that do to the reactivity of the fuel? And it's not that easy to predict it. Okay, it will have some effect. We know that including the double bond here is going to lower the reactivity, but by how much? Okay, if this allyl moiety isn't contributing at all to reactivity, then you would expect possibly that the molecule will behave like propane. That's really the thing. So does it behave like propane? And the answer is no. Okay, because, should I stand here?
No, I'm just going to turn that off.
Okay. Okay. So it doesn't behave like propane, because propane would be even less reactive than butane here. So there is contribution of that allylic part of the molecule to reactivity, but it certainly does inhibit. Okay. There's another thing here, and I'll come back to it later. You can see 1-butene is actually faster than N-butane or N-pentane at higher temperature coming out here. Okay, so why would that be? Maybe we come back to that. Okay, I don't know. I wonder. Maybe if I stand here, it might be better. Okay, so here we have a situation we've just talked about, but here's another molecule, and now we have 2 double bonds in the molecule, but they're separated by a regular carbon atom in between, but it's not a regular carbon atom. It's a super allylic, okay? Because now we have resonance either side of the molecule. So it's actually not the same as a regular allylic hydrogen atom. It's even weaker again to abstract, okay? And actually, trying to come up with good thermochemistry of species for these kind of molecules, I had a PhD student of mine study this, do ab initio calculations. We published a paper last year in Combustion and Flame on this. So you could have a look at that. The student's name was Yang Li, L-I. So if you look for a paper by Lee and Curran from last year, if you go to the our website, you'll see the listing of the paper there, and you can find that. So we talk about different types of allylic hydrogen atom and the bond association energies associated with those. Okay. Okay, so the outlook, kinetic mechanisms for ever larger fuel molecules are being developed due to increasing computational ability. We had that. Okay, there's a lack of focus on accuracy of thermochemistry. The active thermochemical tables is a very good start, but we need more than the heats of formation. Okay, and experimental measurements and accurate quantum chemistry calculations of important reactions involved in the C0, C4 system are vital for accurate predictions of all fuels at high temperatures and for flame speeds. Okay, for sure. And rate rules are useful in building mechanisms for large molecular weight fuels. Okay, so we have all that. Okay, so the rate constants for larger molecules can be calculated with increasing accuracy due to increasing computational ability, which is good. Okay, so that's where I should have finished yesterday. So we move on to the final day. Okay, so we've really now just focused on the chemistry at high temperature. What about the chemistry at low temperatures? Okay, how do we deal with that? Okay, and as I said yesterday, there's, I don't know, 15 or 16 more reaction classes that have to be considered relative to high temperature chemistry. So there, for high temperatures, there was just about 9. Okay, so the chemistry is quite a bit more complicated. There's a lot more reaction classes to be considered for low temperatures. Okay, and this is a slide I include. So I've been focusing the attention all the time on alkanes. Okay, but actually, the same analysis can be applied to oxygenated species. Okay, so this is a reaction flux analysis that are, well, it's not a reaction flux analysis as such, it's just the reaction scheme for dimethyl ether oxidation that I published many years ago. Okay, so dimethyl ether can cleave an OO bond at high temperature given methoxy plus methyl radical, or undergo hydrogen atom abstraction, generating the radical, which then can decompose to give formaldehyde plus methyl at high temperature. So the chemistry is quite simple. But one thing I'd like to point out here, look, you get lots of methyl radicals. So again, methyl peroxy chemistry is going to be important at intermediate temperatures for dimethyl ether. Okay? So we have this radical, we can add to molecular oxygen, and we form the alkyl peroxy radical. And that can undergo an internal hydrogen isomerization, forming the hydroperoxy alkyl radical, just like in an alkane. So here's our R, here's our RO2, here's our QOH. And that QOH can undergo beta scission, okay? It doesn't really form a cyclic ether or an olefin plus HO2 in this case, because there's no 5-membered ring. There's just a 6-membered ring, okay, to give 2 formaldehydes plus OH, right? Or the QOH can add to molecular oxygen again. We get the hydroperoxy alkyl radical that can undergo isomerization, leading to the formation of the carbonyl hydroperoxide plus OH. Okay? The carbonyl hydroperoxide can cleave the OO bond, given the carbonyl alkoxy radical plus OH. So again, from one fuel radical, we get 1, 2, 3 radicals, chain branching. Okay, in exactly the same way as we would in an alkane. Okay, so, and I'll be coming, I might come back to this, I'll certainly refer back to this later when I'm talking about the difference, the similarities and contrasts between hydrocarbons and oxygenated hydrocarbon fuels. Okay, but you can, for oxygenated hydrocarbon fuels, you can still consider the chemistry in a very similar way that we do for alkanes. Okay? The rate constants might be somewhat different, but certainly the scheme is very similar. Okay? And the underlying chemistry is similar. Okay? Now, I spoke a little earlier and a bit yesterday as well about correlations. You know, you have the Evans-Polyani relationship and so on. So typically, for instance, and I've said this already, for stable alkyl hydroperoxide species, to break this OO bond, the bond association energy is weak. It's 43 kilocalories per mole. And typically, we use a rate constant of about 4 or 5 or 1 times 10 to the 16 for the frequency factor, and an activation energy of about 43 kilocalories per mole. Here, it's a half a kilocalorie per mole lower. Okay, so in our mechanisms then, for all hydroperoxide decomposition reactions, we use a rate constant of about this value, okay, within a factor of 2 of that, okay? What about bimolecular initiation reactions? There's a good paper here I recommend you look at. I've included the citations throughout. If you look at fuel plus O2, giving you alkyl radical. Here's Ray Walker again. He studied these radicals, these reactions, I should say. And for alkyl radical, H atom abstraction from alkanes by O2, producing an alkyl radical, he recommends a rate constant of 7 times 10 to the 12 with an activation energy equal to the heat of reaction. Okay? So the heat of reaction is just the heat of formation of the products minus the heat of formation of reactants. Okay? And that's the rate constant used for all these types of reaction. And here I show propane. I referred to this a little bit earlier. Okay? But for propene, the frequency factor decreases by an order of magnitude. Why? Because the radical that you generate is resonantly stabilized. You lose a rotor in the product. And so you had 2 rotors here starting. You end up with 2 rotors. But for propene, you had 1 rotor, but you lose it in the product. Hence, the frequency factor is an order of magnitude lower. Okay? And that's true if you abstract any allylic type hydrogen atom. The frequency factor is going to be lower because of that. But your activation energy is also going to be lower because, again, it's going to depend on the heat of reaction. It's going to be the heat of formation of products minus the heat of formation of reactants. But these are rules that you can use to estimate the rate constants for these types of reaction. Okay. One thing I want to mention now, and I didn't go into it yesterday. So here we have a 6-membered isomerization. And for 6-membered ring isomerizations, okay, is it, okay. Okay, for 6-membered isomerizations, these molecules typically go on and add to molecular oxygen in a second addition, leading to chain branching. Okay? However, these 5-membered rings don't form the QOH, as I said yesterday. They give you olefin plus HO2, typically. Okay? So 5-membered rings don't give this QOH. They give the olefin plus HO2, right, directly from the transition state. Okay? Whereas the 6-membered ring does give you the hydroperoxy alkyl radical. The hydroperoxy alkyl radical can then add to molecular oxygen and go to chain branching. Okay? The 7-membered rings, and I should have it here. I apologize. 7-membered rings, I don't have the slide, but the 7-membered rings actually go on. They form the hydroperoxy alkyl radical, but that hydroperoxy alkyl radical can go on to give cyclic ether plus OH. Okay? So 6-membered rings typically go to chain branching. 5-membered rings go to propagation, giving you an olefin plus HO2. And 7-membered rings also go to propagation, giving you cyclic ether plus OH. That's a very important message in low temperature chemistry. So if you have a molecule then, you could nearly predict its reactivity by just looking at its structure, right? And saying, okay, how many 5-membered rings will this molecule generate? How many 6-membered rings will it generate? And how many 7-membered rings will it generate? Okay, during the isomerizations. You could then, I'm sure, draw a correlation. I don't know if anyone's done it yet. Professor Dreyer here has been talking about those kind of things for many years now, but I haven't seen it published yet. Okay, but you could draw up a correlation that would predict it pretty accurately, I believe. Okay. I showed you this yesterday where we have a table, the table here then of 5, 6, and 7-membered ring rate constants. Okay, how the frequency factor decreases by an order of magnitude as you tie up the rotor, and then the activation energies change because of the ring strain. Okay, and then of course we had Stephanie Villano did these calculations. I went through this yesterday, and she has the correlations again. So we can have rate rules now for the 5, 6-membered ring, primary, secondary, and tertiary hydrogen atom abstraction. Okay, with modern rate constants included there. Okay, there's one thing that, so here, if we go back to the table here, so the dashed line are the recommendations that I had in the papers that I published for N-heptane and isooctane. Okay, they're of the order of these dashed lines. However, the solid line are the rate constants that calculated in the Villano, Carstens, and Dean calculations. And they're 40 times faster. 40 times is a lot in rate constant. And it's going to make the system quite a bit faster. Okay? So, and this is for this isomerization here, the 6-membered ring, 1, 2, 3, 4, 5, 6. Okay? So it's going to significantly affect. So here I have this slide now. I apologize, I should put it in earlier. Okay? But I had prepared it. So here we have this, instead, traditionally, as I said, I think these were included as a hydroperoxy alkyl radical, and then this species was allowed to beta scission, breaking the CO bond here, forming the olefin plus HO2. Okay? But now it's been found through ab initio calculations that it goes directly. There's enough energy in the transition state here to lead directly to the olefin plus HO2. Okay? So it's written now as RO2 gives olefin plus HO2. Okay? Okay, and then this is just illustrating that 6-membered rings go on to chain branching. Okay? But 7-membered rings here, so here we have an example of a 7-membered transition state ring. We get the hydroperoxy alkyl radical, and that hydroperoxy alkyl radical has a relatively facile, you see, now it's a 5-membered transition state ring leading to a cyclic ether plus OH. Okay? What about, why don't I talk about 8-membered transition state rings? I keep talking about 5, 6, 7-membered rings. I don't really talk about 4-membered rings or 8-membered rings. Why not? Why? So the answer was they're statistically unlikely to occur, which is correct. Why? Yeah, very high activation energy, and so won't be competitive with the 5, 6, 7. What about an 8-membered ring? Do you think there'd be much ring strain in this moiety? Not a lot, okay? But no. What happens, the frequency factor as you go up in ring decreases by about an order of magnitude. So again, when you go to the 8-membered ring from a 7-membered ring, you've dropped another order of magnitude. Okay? So here, the activation energy would probably be comparable with a 7 and a 6 and a 7-membered ring. Wouldn't be that much different. But the frequency factor relative to a 6-membered ring would be 2 orders of magnitude lower. So it's not going to compete.
Isn't the
Yeah, but it's really related to entropy change. Remember?
so it's
Yeah, entropy change for reaction. It's very, and always remember, I think that it's the best analogy I can come up with. Gibbs free energy and going across the room. Just think about that and how that's linked with rate of reaction. Okay? So what's determining how fast I get to the other side of the room? My entropy change. What determines whether I get there without any obstacle? The enthalpy. Okay? Activation energy. So if I go in this trajectory, no barrier. If I go in this trajectory, I have to get over the rostrum. Okay? So just bear that in mind. It's a very nice way of thinking of it, in my opinion. So I have them here now, finally. So the fate of five-membered rings, five-membered ring transition state rings will end up in a propagation, right? Six-membered rings will go to chain branching, okay? Just because of the nature of other options that are available to it, okay? Six-membered rings, by the way, this species can give a cyclic ether. So when we form a cyclic ether, so this oxygen atom can rotate, and these four-membered ring can rotate around so that you can generate a bond between the carbon and the oxygen, eliminating OH. But if we look at that, that's a 1, 2, 3, 4-membered transition state ring. How's that in terms of ring strain? High. So the Ray constant for that's going to be low. It's an option, but it's going to be very low. Okay? In the five-membered ring, here, if we think about it, we could have the same. We could have some sort of a rotation around here, the oxygen atom becoming proximate to the carbon, generating a bond, but that's going to be a three-membered transition state ring. Even higher ring strain and even less likely. Okay? So the five-membered ring, it's more facile to produce olefin plus HO2. So that's what it does.
But for a three-membered ring, wouldn't the frequency factor
Very high.
be very high?
Yeah.
So wouldn't-
But the activation energy is so low or so high that in the temperature range in which these are actually produced, it won't happen. If that makes sense. Because you're in the 600 to 1,000 Kelvin range. Okay? By the time the frequency factor will dominate, the species isn't produced anyway. Okay? So you're hooshed. Okay? So the six-membered ring, we could have a four-membered transition state ring, which would then give a cyclic ether plus OH, but that has a very high activation energy, and so it's much easier to add molecular oxygen and go to chain branching. Okay? So the message here is, look, five-membered rings give olefin plus HO2, six-membered rings go to branching, and seven-membered rings typically go to cyclic ether plus OH. Okay? I think I added these slides after I prepared the notes. Okay? So it may not be in your thing, but I've been going on about it now for the last 15 minutes, so I think that, oh, they're all there. Okay, so the message is there. Okay, that's good. Okay, so now, okay, I want this is of concern, right? So, and I'll show you in a minute what I'm talking about. So here, these are the Ray constants that I was recommending in the N-heptane isooctane papers, right? These are Ray constants that are calculated from ab initio. Okay? They're 40 times faster. And that's just one example. That's an example of them all. They're all in that range. Okay? If the Ray constant for isomerizations should be 40 times faster, then that means that the reactivity of the system is going to be substantially faster if I use those Ray constants. Okay? So what's that going to do to my mechanism predictions? Okay? And so I had some very good students. So Emma Silk, she worked with me in the mid-noughties, okay? Graduated, I think, around 2005 or 2007. And John Bugler then came about a decade later, okay? And he worked on so this is John, he worked on the pentane isomers that I've been talking about, okay? And this is Q.N. Zhang, a postdoc who left me, went to Livermore, and now is working with Convergent Science, okay? So we published a paper where we looked again at the pentane isomers, and that was published in 2015. So let me just go back. So I worked on N-heptane, isooctane in 1998 to 2002, okay? They were published, those two papers. Then Emma came, and she was working on she published work on the heptane isomers and data that we measured in the rapid compression machine. But I also asked her to look again then at the low temperature chemistry of N-heptane. Okay, so I'm going to show you now the results of her simulations in the mid-noughties, right, working my group. Okay, so this is just the general scheme again, and our understanding of the low temperature chemistry. So it's similar to the slide that I've been showing you. So this would have been published in our N-heptane or isooctane papers. So a fuel giving us alkyl radical, add alkyl radical adding to molecular oxygen giving RO2, the RO2 isomerizing to QOH. Okay, there's a little message here. I think I've said it already. We didn't have RO2 going directly to olefin plus HO2. But what we did have was then the HO2, sorry, the QOH going to cyclic ether plus OH, olefin plus HO2 are by decision products. Ironically, or fortunately, or whatever, in the system, the hydroperoxy alkyl radicals that were performed here that could give 5-membered rings, they gave you olefin plus HO2 anyway. So the net effect was the same, right, ultimately. So it didn't, putting in the RO2 going directly to olefin plus HO2 didn't affect our mechanism performance hugely, okay? There will be an effect I'll show you later, and you'll see it, okay? But it didn't affect it hugely, okay? Then this adds to molecular oxygen. We get O2QOH, we get carbonyl hydroperoxide, and we get the second decomposition. So we go into branching, okay? So it's a little bit simpler system than what I showed you earlier with the colors and so on, okay? The reason for that is we added the colors later because here's our system. We have alkyl radical adding to molecular oxygen given RO2. The RO2 can give isomerized to QOH, give olefin plus HO2, cyclic ether OH. And this, the hydroperoxy alkyl radical can add to molecular oxygen again. Okay? So if we now come down here to this part, this QOH can add to molecular oxygen, giving us peroxy hydroperoxy alkyl radical. Okay? But this species, the same as an RO2, could give you an olefin plus HO2. Right? I'll show you a schematic in a minute. Okay? But we didn't have this in the mechanism. Okay? This can isomerize to this species, similar to QOH, and this species can give you a cyclic ether or other beta decision products, or go on and give you a carbonyl hydroperoxide plus OH. Okay? So it's a parallel chemistry to what we had already included. And if you're going to be complete, you should consider them all. I don't know, where did it go? I don't know. Oh, I found it.
Thank you.
And you got a bonus. Okay. So if you're going to be complete and understand everything, you should include everything and let everything happen so you can see what is actually controlling the chemistry, right? But these were excluded, and they should have been included. Okay. So when Emma came, we said, okay, let's look at adding different reactions to the system. So let's look at alternative H-atom isomerizations from here. And I'll show you what I mean by that in a minute. Okay? So there were all these, I'll go into them in more detail. They're meaningless, just me showing you on the board. They're P's and Q's and so on. Let's look at what I'm talking about. Okay, so here we have N-heptane. Okay, we've abstracted a hydrogen atom, a secondary hydrogen atom. We've undergone isomerization, and we've added the radical to O2 again. So we're at the O2-QOH stage. Okay, this O2-QOH, so what we did was we said, okay, this species can abstract a hydrogen atom from here. Okay, why? Right, because this carbon atom is bonded to a carbon, but it's bonded to an OOH group. What does this OOH group do to the CH bond? It weakens it, okay? And it weakens it to the point that the Ray constant for abstraction of this hydrogen atom on this carbon is lower by 3 kilocalories per mole relative to a regular secondary hydrogen atom where the OOH wouldn't be bonded to the carbon. All right? So we only allowed this to happen. So we had this transition state, a 7-membered transition state. We formed this carbonyl hydroperoxide plus OH. Okay? But we didn't allow any other isomerizations to occur. But can other isomerizations occur, do you think? Yes, of course. So what could occur? What would be a good one? Yeah, abstract someplace else. So here, you have actually a very facile 6-membered ring that we've completely ignored, right? So here, there's a hydrogen atom here. Well, there's 2 of them, actually, right? We could have a 6-membered ring, okay, abstract that, and we get this radical species here. If we have a radical species here, though, that's going to cleave this CO bond here. So the electron is going to move in here, electron move here. We're going to get an olefin plus HO2. Okay? Didn't consider it in the N-heptane isooctane mechanism. But perfectly capable of happening. Actually, it's probably more likely to happen than the 7-membered isomerization. Because remember, the activation energy is low, and the frequency factor is an order of magnitude higher for the 6-membered ring. Okay? So 6-membered seem to be sort of optimal Ray constants at low temperature. Okay? Yet we didn't consider it. Also, if we arrive here, we could get a cyclic ether, okay, plus OH. And that cyclic ether then can decompose. So we included that reaction class in the mechanism. Okay, so I was saying this to Emma. I said, look, we should really consider everything, explore what happens to chemistry. So here's the black line I'm going to show you each time is the baseline model. And the red line is going to be the change that happened when we added that chemistry to the mechanism for N-heptane. Okay, so this is for N-heptane oxidation in air at 13.5 bar. Okay, and you can see we added these alternative isomerizations. Okay, so we allowed the 6-membered ring, the 5-membered ring, any one that could occur, we allowed it to occur. We included Ray constants at the same rate that we allowed other similar isomerizations to occur, and added that to the mechanism, and here's the prediction. So the mechanism became too slow at low temperature and became faster at higher temperature. Does that make sense? What's happening? Here, instead of us producing a carbonyl hydroperoxide plus OH, we're producing this species, okay, which is this olefinic hydroperoxide plus HO2. This olefinic hydroperoxide will eventually cleave the O bond, just like this one will, to give our carbonyl an olefinic alkoxy radical plus OH. This will give us a carbonyl alkoxy radical plus OH. So the only difference is we're getting a HO2 in this case, we're getting an OH in that case. Okay? So what does that do to our reactivity? It decreases it at lower temperatures because HO2 can't go anywhere, right? HO2, okay, it will abstract a hydrogen atom from the fuel. We're going to get another R, and we'll get H2O2. H2O2 won't give us much heat release, and it just sits there until the temperature reaches about 850 Kelvin, and then the OO bond breaks because of that activation energy for OO bond breaking. Okay? So H2O2 is going to be stable, right? So reactivity decreases up to about 850 Kelvin. And then above 850 Kelvin, reactivity increases. Why? Because now the HO2 is leading to H2O2, which gives two OHs. Okay? So it makes perfect sense, actually. Okay? And you could, if you think about it before you even do the simulation, you'd say, this is what's going to happen. Right? And that's what you see. Okay. It's even worse. Right. So here I add another reaction class. So we added these alternatives. So from these species, we produce these cyclic ethers plus OH at the same rate at which we would produce a cyclic ether in the first QOH. Okay? Similar rate constants. Okay? And now the system moves here to the blue line. Okay? So do we really understand low temperature chemistry? Not great. Okay? So, okay. Also, then I was aware that there were calculations. So Villano and Green and Miyoshi and these guys, I'll be talking about them in a minute, they weren't the first people that ever did ab initio calculations on RO2 to QOH isomerizations and so on. There were other ones performed before that. So Samanthi and Green published some ab initio calculations, CBS-QB3 level of theory. Okay? The rate constant for isomerizations, again, were an order of magnitude faster than the ones that I was recommending in the model. Okay? And if we put in their rate constants for these isomerizations, RO2 to QOH and O2 to QOH giving us carbonyl hydroperoxide plus OH, this is, so we're order of magnitude faster. Okay? So now we really don't know what we're talking about. Okay? Really, really, really don't know. Okay? So this is all work that Emma did in her thesis. Okay? We didn't ever publish the thesis. Okay? For obvious reasons, because it didn't agree very well with experiment. Right? Okay, we also thought of other things. What about if we have the hydroperoxy alkyl radical, we can isomerize them just like you can alkyl radicals. And if you inter-isomerize these into other QOH radicals, okay, which can happen for long chain molecules, fairly facile. Okay? And we included that. Actually, it made no change. So the agreement was the same. Okay? So that had no effect on reactivity. Okay? So that was one place where we saw no effect. Okay? Then this was new. Okay? So the RO2 giving us olefin plus HO2. Actually, the first people to show this was in 2003, Tim Barkholz, Joe Bazzelli, and I don't know the first name here. They presented this at the US section meeting it was held in Chicago, okay, in 2003. And they gave rate constants for these RO2 giving olefin plus HO2, okay? If we included those in the model, actually it made things a little bit slower. But as I said, it didn't have a huge effect because the net effect on our mechanism was very little in terms, we had 5-membered rings giving us hydroperoxy alkyl radicals, and then those hydroperoxy alkyl radicals gave us olefin plus HO2 anyway. Okay? All it did was cut out the middleman, the hydroperoxy alkyl radical, and RO2 giving us olefin plus HO2 directly for the 5-membered rings. Okay? And there wasn't much change in our mechanism prediction. Okay? Then there were updated values from Chitral Nayak in his PhD thesis. He was working, so Tony Dean this work, Tim Barkholz at the time worked at ExxonMobil here in New Jersey, and Joe Bazzelli consulted at ExxonMobil a day a week or something like that, or a day every 2 weeks. And so the work that was done here was actually funded by ExxonMobil. And Tony Dean was Chitral Nayak's supervisor at the Colorado School of Mines. And he had just left ExxonMobil. So they were all interested in the same thing at the time. And that's why all of this was done. Okay? And these rate constants are slightly different. And they were a little bit faster. And hence, the reactivity decreased a little bit more. Okay? So it was just showing you a little bit of the uncertainty in the rate constants too. Okay? But I think everybody would agree this line doesn't match the experimental data very well. Okay? And so I was a little bit concerned, okay, that did we really understand low temperature chemistry? Okay? So that was the mid-noughties, right? And I didn't have much time or funding to work on it. Okay? It wasn't where it was always of concern to me, but to get the resources to do it, I wasn't able to for quite some years. Okay? But eventually, John was able to spend some time on it. And fortunately, he sorted it out. Okay? So now I'm going to show you how we sorted it all out. Yeah. Cumulative. So
did you ever investigate?
Yes, we did, but just for the narrative. So I was asked, are these effects cumulative? And the answer is yes. And did we ever explore just doing each one individually? And the answer is yes also. But for this narrative, I just wanted to show you, the cumulative effect of everything to keep it short. Okay? So yes is the answer. We explored everything. And probably in Emma's thesis, it's all there. Okay, if you want to get a copy. If you ask me for it, I can give you a PDF. I can send you a PDF. Okay? So we looked again at everything. Okay? But really, okay, I have up in here all the different reaction classes and the rate constants. But you know what was behind it all, ultimately? Thermochemistry. Okay? The thermochemistry. And it's critical to accurate prediction. And even today, we don't really have accurate enough thermochemistry for all these low temperature species to do all the fuels really accurately. Okay? And that's, as I said to you on Monday, it's one area that I'm very interested in right now. And we're working with Stephen Klippenstein to try and get really accurate thermochemistry for alkane, low temperature alkane combustion species. Okay? So let me just, this then is a synopsis, and you can look at yourself in the future. It's more for your reference. It's too much detail for what I'm going into now. I'll go through it nice and slowly, and it'll be better as I go through it. Okay? But I just want to say, look, Comandini, he's worked with Jeff Mannion at NIST. They looked at alkyl radical decompositions. Actually, fortunately, it was for pentyl radical decompositions. Okay? Professor Miyoshi in Japan looked at alkyl radical plus O2 rate constants. And I've shown you this already. Stephanie Villano looked at all these ones. So RO2 giving you olefin plus HO2, RO2 isomerizations, hydroperoxy alkyl giving you olefin plus HO2 also, cyclic ethers plus OH, and bed decision products. All of those. Okay? And then what about the RO2 alkyl radical plus O2? So you consider, remember I said consider the hydroperoxy alkyl radical like an alkyl radical, and that addition to O2, giving you the hydroperoxy alkyl radical, and then the isomerizations. So these were normally considered by analogy with RO2 giving us QOH. And I'll illustrate that to you as well. Okay? Okay, so as I said, we're 40 times faster, and so it's going to make a big difference. Okay? We also included new reaction classes, and this is just showing you again what I've showed you. So by analogy with RO2 species, we can have this, if you consider this RO2, giving us olefin plus HO2, the hydroperoxy alkyl radical as an alkyl radical, okay? Or this RO2 giving us POH by analogy with RO2 to QOH, and then this species giving us olefin plus HO2, cyclic ether, or other beta decision products, just like the hydroperoxy alkyl radical from the first edition of molecular oxygen. You can get the same thing from the second edition. Okay. Now, there's one thing here I want to show you as well. Okay? I'm almost ready to take a break because I'm going to build it all up and then we're going to take a break and then we'll solve it after the break. Okay? So, here's our, actually the molecule that I said that it's the first one that gives you a gauche interaction. Okay? But if we abstract the tertiary hydrogen atom, which is the easiest one to abstract, we get the alkyl radical, that adds to molecular oxygen, we form the RO2, and then we have a 1, 2, 3, 4, 5, 6-membered ring giving us the QOH, the most facile one, and it's the fastest one that will occur. And then we add, so this is our QOH, we add to molecular oxygen, and we get O2 QOH. Okay? But now, here we have a radical site here, one, so we want to now abstract a hydrogen atom from this carbon, which is bonded to the OOH. But unfortunately, there is no hydrogen atom on this carbon bonded to the OOH. It's 2 carbon atoms. So in the old way of doing things, that went nowhere, right? Is that good chemistry? Good practice? No. Because it shouldn't go nowhere, because we can abstract a hydrogen atom here or a hydrogen atom from there and allow the chemistry to progress. Okay? We shouldn't just stop it there. Okay? So in the old way of doing things, we didn't. It was a dead end. And so it just went backwards, didn't go anywhere. Right? So we added all that. Okay? So let me take a break. Okay? And when we come back, I'll go through what we actually did to try and solve everything.